part we defined Catalan numbers and we showed some identities related to them, what their size is and exactly how big they are. This time, let's look at some results regarding the Catalan numbers. Theorem. The Catalan numbers satisfy a recurrence relation for n greater than or equal to 1. Cn is equal to C0 times Cn minus 1 plus C1 times Cn minus 2 plus dot 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 Cn minus 1 times C0, which is equal to summation k is equal to 0 to n minus 1 CFK CFn minus 1 minus k. Okay, and this shouldn't come as a surprise because we know that in the chapter 7, section 7.6, we saw that Catalan numbers are related to the number of triangle divisions of n plus 1 gone into triangles, and there we used this exact recurrence sequence to get that identity, right? So we are going to use a different proof for this. You have already seen one proof. Let us use a proof by partial summations. Proof. So define as before, let an is equal to set of all permutations, set of permutations of multiset, set of permutations a1, a2, all the way up to a2n of the multiset n times 1 and n times negative 1 such that with all the partial sum, which has all partial sums greater than or equal to 0, with all partial sums Si greater than 0, greater than or equal to 0 for, well, for I in 1 to, oh, actually maybe 0 to whatever, 0 to 2n. Okay, so this is the same thing that we defined previously. Then we can say that, oh, given a sequence, given a1, a2, dot dot dot, a2n inside an, well, because the partial sums have to be positive, a1 has to be equal to 1, and because s of s2n is equal to 0, there is some t, define t is equal to minimum of I, such that, well, a1 is 1, so s1 is equal to 1, s of 0 is 0, s0 is equal to 0, such that, well, 2 is smaller than or equal to I is smaller than or equal to n, and s of I is equal to 0. Okay, this is the first time where my sequence comes back down to 0. This is called the landing number. Okay. And so visually, what does it look like? Well, here's my sequence 1, and then it's going to do some random nonsense, maybe go up and down and down. Then it will hit 1 again, come down to 0, and then it might do whatever it wants to do, go up, down, whatever. Sure, these, whatever, just assume this is 1 and this is 1, and whatever, these peaks are also 1 level, whatever. Okay, So this is going to be my landing number ST. Okay. And then this is going to be S2N, which whatever how long it is going to be. And so I see that ST minus 1 is also equal to 1. So S1 is equal to 1, ST minus 1 is equal to 1. Okay. And T has to be even. Note, T is even, right? S1 is equal to A1 is equal to 1. ST minus 1 is equal to AT minus 1 is equal to 1, right? And A of T is equal to -1. Oh, sorry, that's wrong. ST minus 1 is equal to 1. AT is equal to -1. I have no idea about AT minus 1. Okay. And so what else I see is between 1 and between 1 and T minus 1, SI is greater than or equal to 1. 1 smaller than or equal to I, smaller than or equal to T. T minus 1, whatever, right? Because if it was hitting 0, then that would have been the minimum place where it hits 0, and that would be my minimum number. So what is happening is that I can look at a new sequence from here to here, right? And that sequence, since it's even, is going to have some length, maybe T minus 1, T minus 2 over 2. Okay, and that is how I'm going to break it up into two types of sequences. Okay, so partition A according to the landing number. According to the landing number. Okay. And for 0, so the landing number can be anything between 0 to 2, between 2 to 2n, right? And so we are going to say let AK is equal to set of permutations in A that have that has landing number 2k plus 2. Set of perms in A with landing number 2k plus 2. And so, therefore, well, by my definition, I have 0 smaller than k smaller than or equal to n minus 1. Okay. So if k is equal to 0, my landing number is still 2. It's not 0. And when k is equal to n minus 1, my landing number is 2n. Okay. Notice that every element of A has to have some landing number. At least it is going to be 2n because that is where it hits back. And everything has exactly one unique landing number. So these AKs, k is equal to 0 to n minus 1, partition A. Partition A, and therefore size of A is equal to summation k is equal to 0 to n minus 1 size of AK, right? And so now we are going to look at how to calculate the size of AK. Okay. So here's my algorithm for calculating size of AK. Take here, construct A1 to A2n in AK in stages. Here's my algorithm that I'm going to use, right? Stage 1, stage to do, and number of choices. In the first stage, I am going to choose what is A1. Pick A1. And surprise, surprise, there is exactly one choice, right? Which is equal to 1. Because my partial sum has to be positive at 1, I have to take A1 is equal to 1. 2, pick the sequence A2 to A t minus 1. Okay, now, note, we will write t is equal to 2k plus 2. Okay, if t is equal to 2k plus 2, this has length exactly 2k, right? This has length t minus 1, t minus 2, which is exactly 2k. And if you look at the figure that we drew before, what is happening is the thing above 1, above the height 1, has to maintain the height, right? It cannot fall below 1. That means it is another sequence. If I cut it off at these green points, it is another sequence which has partial sum positive at every single point. So that sequence has to belong to CK. 3, pick AT. Well, surprise, surprise, there's only one choice because it has to land back at K, right? And K is at T, which is 2K plus 2. So it has to be -1 there. And for the stage 4, pick the sequence, pick AT plus 1 dot 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 A to N. Length of this is going to be, well, the total length of everything is 2n. So the length of this is going to be, I subtracted 2, so the total length is 2n minus 2, which is going to be half. So k n minus 1, n minus 1 minus k, right? And that means the total number of sequences I can have in AK, the first half has ck choices, the second half has cn minus 1 minus k choices. So size of AK is ck cn minus 1 minus k. And therefore, cn is equal to cardinality of A, which is summation k is equal to 0 to n minus 1, cardinality of AK. And we just proved that is equal to k is equal to 0 to n minus 1, ck cn minus k and 1 minus k. Okay. So let us use that to do an example. Let us see an example where we are using these, right? So suppose you have an n cross n chessboard or a city block n cross n. Okay. So you have some lots and lots of columns, rows, and lots of columns. Okay, you're starting from your point A and you want to go to point B. Okay, now assume that you do not want to cross the diagonal. Maybe there's a river that flows through here which actually has no bridges and the town is split into two. So you can either go from the top or the bottom. In the middle, you cannot cross. So you have to stay either above the diagonal or below the diagonal. How many paths do we have? Well, if I look at it, what is happening? I can say that, oh, I will turn this figure on the side, right? And then it becomes, I can okay, let me say this. Each step, well, let me phrase the problem first. Problem. So n columns, and not columns, and vertical roads, and vertical roads, and this is going to be n horizontal roads. Problem: want to travel from A to B without crossing the diagonal. Okay. Answer? Well, every step has to be either north or west. Every step is either north or west. Okay. I am going to give them values. I am going to say north is 1 and west is -1. Okay. So I am not allowed to cross the diagonal, but I am allowed to touch the diagonal. Okay. So I am allowed something like this or something like this. Okay. Something like this. Not okay. Right? I am going to give them values 1 and -1. And then number of paths is equal to number of sequences of length to n, sequences of length to n, made of length to n of the multiset n times 1, n times -1, which are whose partial sums are all non-negative or all non-positive. Right? Because if I go above, I have to stay above, right? That means my partial sums have to stay positive. If I go below, I have to stay below. That means my partial sums are always negative. Okay, and so I know, therefore, number of paths is equal to 2 times number of such steps, which is 2 times number of sequences of length, number of permutations, perms of length to n of n times 1 comma n times -1. Well, non-negative, non-positive, the number of sequences is going to be the same thing, right? Take a sequence up there, flip it completely, hit everything with a negative. That gives you a sequence with all non-positive partial sums, with all partial sums non-negative is equal to 2 times Cn, right? And therefore, this is equal to 2 times 1 over n plus 1 to n, choose n. Okay?